Close your eyes for a moment and imagine standing on a world where the sun fills half the sky. There is no wind, no atmosphere, no sound, only light, harsh, white, relentless, pouring over a cracked metallic landscape that has not changed for billions of years. This is Mercury. From a distance, it looks simple, grey, scarred, silent, a small rock trapped too close to the sun. But Mercury is not as quiet as it seems. It is shrinking. Deep beneath its ancient surface lies a massive iron core, far larger proportionally than Earth's. Long ago, that core was molten and restless. Over billions of years, it has cooled. And as metal cools, it contracts. When Mercury's core began to solidify, the entire planet responded. The crust had nowhere to go. It buckled. It cracked. It folded upward into enormous cliffs that stretch for hundreds of kilometers across the surface. Mercury has physically become smaller than it once was, not in a violent collapse, not in a sudden disaster, but slowly, quietly, inevitably. Tonight, we explore how this tiny planet is aging from the inside out, how heat escapes, how rock compresses, and how even a world so close to the sun cannot escape the laws of physics. If you enjoy deep, calm journeys through real space and real science, make sure to subscribe to Theories Before Sleep, where we let the universe speak softly. Now, let's begin. To understand why Mercury is slowly destroying itself, we have to begin at the very beginning, long before cliffs formed, long before its surface cracked, long before it became the smallest planet in the solar system. About 4.6 billion years ago, the solar system was not made of planets. It was a rotating disk of gas and dust surrounding the young sun. Within that disk, particles collided and stuck together, forming larger and larger bodies. Over time, gravity shaped these growing clumps into planetesimals and eventually into planets. Mercury formed in the hottest region of that early disk. Close to the sun, temperatures were extreme. Light elements and volatile compounds struggled to remain stable. Ice could not survive. Many gases were stripped away. Only the most heat-resistant materials, metals and rocky silicates, remained in large quantities. This environment already set Mercury on a different path from Earth, Mars, or Venus. As Mercury grew, heavy elements such as iron sank toward its center through a process known as differentiation. When a young planet is still molten, gravity pulls dense materials inward. On Mercury, this process was unusually efficient. Today, Mercury's iron core makes up roughly 85% of the planet's radius. That is extraordinary. For comparison, Earth's core accounts for about half its radius. Mercury is essentially a giant metal sphere with a relatively thin rocky shell wrapped around it. Why did Mercury end up with such a massive core? There are two leading explanations. The first suggests that Mercury formed in a region already rich in metal and poor in lighter materials. In this view, the inner solar system's high temperatures caused lighter silicates to vaporize or disperse, leaving behind iron-rich building blocks. The second possibility involves violence. Early in the solar system's history, collisions were common. Planets were struck repeatedly by large bodies. And because the crust is relatively thin compared to the massive core beneath it, the stress had nowhere to dissipate gradually. It had to break the surface. When NASA's Mariner 10 spacecraft first flew past Mercury in the 1970s, it revealed a heavily cratered world. For decades, scientists thought Mercury was geologically inactive, a frozen relic of the early solar system. But the full picture only became clear in the 21st century. The Messenger spacecraft, which orbited Mercury from 2011 to 2015, mapped the planet in extraordinary detail. High-resolution images showed enormous cliff-like structures stretching hundreds of kilometers. These features are called lobate scarps. They look like giant wrinkles across the planet's surface. Some are over a kilometer high. They form when one section of crust is pushed up over another along a thrust fault. This only happens under compression, not stretching, not volcanic expansion, compression. The entire planet has been slowly squeezing itself. But here's the crucial point. These scarps are found all over Mercury, not in one region, not near a single basin. They are global, which means the cause must be global. That brings us back to the core. Mercury's iron core is still partially molten today. Unlike the Moon, which cooled more completely, Mercury retains a liquid outer core layer. This is confirmed by measurements of its magnetic field. Yes, Mercury has a magnetic field. It is weak compared to Earth's, but it exists. That magnetic field tells us that liquid metal still moves inside the planet, and that movement generates a dynamo effect. But the core is not as hot as it once was. Over time, more of it solidifies, and as it does, the contraction continues. The crust does not collapse suddenly. It adjusts slowly. New scarps can form as old ones accumulate stress. Recent crater counts suggest some of these tectonic features may be geologically young, possibly less than 1 billion years old. In planetary terms, that is recent, which raises an important possibility. Mercury may still be shrinking today, not dramatically, not visibly, but measurably. This is what makes Mercury unique among the rocky planets. Earth's tectonics are driven by mantle convection and plate movement. Mars shows evidence of past volcanic activity, but lacks global compression features like Mercury's. The Moon has small contraction scarps, but on a much smaller scale. Mercury's entire geological identity is shaped by internal contraction, and this contraction traces directly back to its unusual birth. A planet formed too close to the Sun, possibly stripped by impact, left with an oversized metallic heart. Everything we see on its surface begins there. In the next section, we'll move from formation to structure in greater detail, exploring exactly how Mercury's internal layers are arranged, how scientists measure them, and why its core behaves differently from Earth's. No repetition, only progression. To understand what is happening inside Mercury today, we need to look more closely at its internal structure. Not just that it has a large iron core, but how that core is arranged, how thick the crust is, and how scientists know these details without ever drilling into the planet. Everything we know about Mercury's interior comes from indirect measurements. When a spacecraft orbits a planet, it doesn't just take pictures. It measures gravity, magnetic fields, rotation, and tiny variations in motion. These data allow scientists to infer what lies beneath the surface. Messenger carried instruments that tracked minute changes in Mercury's gravitational field. By measuring how the spacecraft's speed shifted slightly as it passed over different regions, researchers could map density variations inside the planet. The results confirmed that Mercury's core is not just large, it dominates the planet. The core's radius is estimated to be about 2,000 kilometers, leaving a relatively thin mantle and crust compared to other terrestrial planets. Above the core lies a silicate mantle, much thinner than Earth's. Above that, the crust ranges roughly between 35 and 50 kilometers in thickness, depending on location. This thin outer shell plays a crucial role in how the planet responds to internal cooling. On Earth, a thick mantle and active convection distribute heat in complex patterns. Plate tectonics continuously recycle crust. Stress is relieved through subduction, spreading ridges, and earthquakes. Mercury does not have plate tectonics. Its lithosphere, the rigid outer layer, is thick and mostly immobile. When stress builds, it does not get absorbed by moving plates. Instead, it accumulates until the crust fractures. Another key difference lies in Mercury's core composition. Evidence suggests that Mercury's core contains not just iron, but also lighter elements such as sulfur. The presence of sulfur lowers the melting point of iron, which helps explain why part of the core remains liquid despite the planet's small size and advanced age. If Mercury's core were pure iron, it might have solidified completely by now. But because sulfur modifies the metal's properties, the outer portion of the core remains molten. That liquid layer moves as the planet rotates, generating Mercury's weak magnetic field. This magnetic field is not as strong as Earth's, but it is significant. It shields the surface partially from the solar wind and proves that internal motion still exists. However, the magnetic field also reveals something else. It is offset. Measurements show that Mercury's magnetic dipole is shifted northward relative to the planet's center. This suggests asymmetry within the core, possibly due to uneven cooling or compositional differences. Cooling is not necessarily uniform throughout the planet. As Mercury loses heat to space, its interior temperature drops gradually. The rate of heat loss depends on conductivity, composition, and thickness of the outer layers. Because Mercury lacks a thick atmosphere, it radiates heat directly into space more efficiently than Earth. There is no insulating blanket of gases trapping internal warmth. Over billions of years, this steady loss of heat has caused progressive solidification of the core. When molten iron crystallizes into solid form, it occupies less volume. That reduction in volume is the mechanical driver of planetary contraction. This process does not occur all at once. It happens slowly, layer by layer, as the inner core grows outward. As the inner core expands, the remaining liquid outer core shrinks. The total volume of the metallic interior decreases slightly. That decrease transmits stress outward through the mantle and into the crust. The crust responds by compressing. Rock behaves differently depending on temperature and pressure. At sufficient depth and heat, it can deform plastically, bending without breaking. Near the surface, however, the crust is colder and more brittle. On Mercury, the outermost layers are rigid, so when compression builds, they fracture. But before we look again at surface expressions, it is important to understand how scientists confirmed that Mercury's core is still partially molten. One method involves measuring the planet's rotation. Mercury is in a 3-to-2 spin-orbit resonance. For every 2 orbits around the Sun, it rotates 3 times on its axis. This unusual rotational pattern produces small oscillations called librations, slight back and forth wobbles. By measuring the amplitude of these librations with high precision, scientists can determine whether the core is solid or liquid. If the core were completely solid and rigidly connected to the mantle, Mercury would wobble less. But observations show larger libration amplitudes than a fully solid interior would allow. The simplest explanation is that the outer core is liquid, decoupling partially from the mantle and allowing a slightly greater wobble. This finding confirms that internal cooling is ongoing, not complete. Another line of evidence comes from topography. Mercury's global shape is slightly flattened at the poles and bulged at the equator, as expected for a rotating body. But detailed measurements of gravity and shape provide clues about internal layering and rigidity. These data indicate that Mercury's lithosphere, the rigid outer shell, is thick. Estimates suggest it may exceed 200 kilometers in some regions. A thick lithosphere means that heat from the interior escapes slowly through conduction rather than active convection. This further supports the model of gradual cooling and contraction. Unlike Earth, Mercury does not have large-scale mantle plumes reshaping the surface today. Most of its volcanic activity occurred billions of years ago when internal heat was greater. Large lava plains visible today were formed during that earlier, hotter period. Over time, as internal heat declined, volcanism decreased. Contraction became the dominant geological force. But Mercury's internal story includes one more important detail. Its core occupies a much larger fraction of its total mass than any other terrestrial planet. This affects not only contraction, but also how the planet responds to tidal forces from the Sun. Because Mercury orbits so close to the Sun, it experiences strong gravitational tides. These tides flex the planet slightly during each orbit, producing small but measurable deformations. By analyzing how Mercury deforms under solar tidal stress, scientists can estimate the rigidity of its interior and confirm the presence of a liquid layer. The combination of gravity data, rotational measurements, magnetic field analysis, and tidal deformation modeling paints a consistent picture. Mercury has a massive iron-sulfur core that is slowly solidifying. As it solidifies, the planet contracts. And because the outer shell is rigid and thick, the contraction expresses itself through crustal compression. This internal evolution is not unique in principle. All rocky planets cool over time. But Mercury's proportions amplify the effect. Its oversized core means that a greater fraction of the planet undergoes volume reduction during solidification. Its small size accelerates heat loss. Its thin mantle offers limited buffering between the core and crust. Together, these factors create a planet where internal cooling directly reshapes the surface. In the next section, we will move from the hidden interior to the visible scars, examining how compression produces specific landforms, why Mercury's cliffs look the way they do, and how scientists determine their age. Each surface feature is a record of stress from deep within the planet, and those records tell a story of ongoing change. When compression builds inside a planet, it does not express itself randomly. Rock responds according to physics, according to pressure, temperature, and the mechanical strength of the crust. On Mercury, the visible result of that stress is written across the surface in structures unlike anything seen at the same scale on other rocky worlds. The most distinctive features are the lobate scarps. From orbit, they appear as long, curved cliffs that cut across craters, plains, and ancient terrain. Some stretch for hundreds of kilometers. Many rise more than a kilometer above the surrounding landscape. Their edges are sharp, their faces steep. They are not volcanic ridges. They are not impact ejecta. They are tectonic faults. More specifically, they are thrust faults. A thrust fault forms when one block of crust is pushed up and over another under compression. Imagine slowly squeezing a thick carpet from both ends. Eventually, the carpet wrinkles and folds. The material has nowhere else to go. Mercury's crust behaves in a similar way, but on a planetary scale. As the interior contracts, horizontal stress accumulates. When the stress exceeds the rock's strength, it fails along fault planes. One section overrides another, creating a scarp. What makes Mercury remarkable is the global distribution of these scarps. They are not confined to a single hemisphere. They are not localized around a particular basin. They appear across the entire planet. This tells scientists that the driving force is global contraction, not regional tectonics. Some scarps cut directly across impact craters. That detail is important. If a cliff slices through a crater, it must be younger than the crater itself. By examining which features overlap others, scientists build a timeline of events. Messenger images reveal that some lobate scarps deform relatively small and geologically young craters. This suggests that contraction continued long after Mercury's heavy bombardment period ended. In planetary science, age is often estimated by counting impact craters. Surfaces with many craters are generally older. Surfaces with fewer craters are younger because they have been resurfaced or altered. When researchers analyzed regions around certain scarps, they found crater densities indicating that some fault activity may have occurred within the last billion years. In geological terms, that is recent. This means Mercury did not shrink only in its distant past. The process likely continued through much of its history. But contraction is not the only visible consequence of internal cooling. As Mercury's interior temperature dropped, volcanic activity also changed. Early in its history, vast lava flows resurfaced large portions of the planet. These smooth plains are visible today, especially around impact basins like Caloris Basin. Lava flooded low-lying regions, covering older terrain. However, volcanism on Mercury appears to have diminished earlier than on Earth. The decrease in internal heat limited the ability of molten rock to rise through the crust. Without sustained mantle convection, volcanic resurfacing slowed. As volcanic forces weakened, compressional tectonics became more dominant. There is another detail that distinguishes Mercury from Earth. On Earth, compression can be relieved in multiple ways. Plates collide and subduct. Mountain ranges rise. Crust thickens in localized regions. Mercury does not have moving plates. Its lithosphere behaves as a single rigid shell. So when contraction occurs, the entire shell must accommodate the strain. This leads to a network of thrust faults distributed widely rather than concentrated at plate boundaries. In addition to large lobate scarps, Mercury also exhibits wrinkle ridges. These smaller compressional features form when the crust buckles under stress. They often appear in volcanic plains where lava has cooled and hardened. Wrinkle ridges are shorter and lower than major scarps, but indicate the same underlying force: horizontal compression. Another feature linked to internal evolution is the presence of hollows. Hollows are shallow, irregular depressions with bright interiors and halos. They are unlike impact craters and unlike volcanic pits. Their edges are sharp, and they often appear in clusters. Scientists believe hollows form when volatile materials in the crust are lost to space. When certain minerals are exposed to Mercury's harsh environment, high temperatures and solar radiation, they may sublimate or break down, leaving voids behind. While hollows are not direct evidence of contraction, they reveal that Mercury's crust contains more volatile material than once assumed. This complicates earlier models that portrayed Mercury as entirely dry and metal-rich. The presence of volatile-bearing minerals suggests that Mercury's formation history may have preserved more diverse materials than expected. Returning to contraction, researchers have attempted to quantify how much Mercury has shrunk. Early estimates suggested a reduction in radius of about 1 to 2 kilometers. Later analyses, incorporating improved topographic data from MESSENGER, indicate that the total shrinkage may be closer to 5 to 7 kilometers. That amount might seem modest compared to Mercury's overall size, but consider what a 5-kilometer global reduction implies. If Earth were to shrink by even 1 kilometer in radius, the resulting stress would be enormous. Entire continents would experience deformation. On Mercury, where the lithosphere is thick and brittle, the stress has been accommodated through widespread faulting. There is no atmosphere thick enough to erode these structures quickly. Without rain, wind, or flowing water to reshape the landscape, tectonic features remain preserved for hundreds of millions of years. This preservation allows scientists to reconstruct the planet's history with unusual clarity. Compression also affects crater shapes. Some impact craters on Mercury appear distorted or truncated by thrust faults. Their circular rims are cut and offset. By analyzing these relationships, scientists determine which events occurred first and how contraction progressed over time. Another aspect of Mercury's surface evolution involves gravitational adjustment. As the planet cools and contracts, its moment of inertia changes slightly. This can influence rotational dynamics and stress distribution. Although Mercury's orbit and spin are strongly governed by solar tides, internal structural changes contribute subtle effects. Thermal contraction does not occur uniformly across the planet. Variations in crust thickness, mantle composition, and core crystallization may cause regional differences in stress intensity. For example, areas with thicker crust may resist deformation longer, concentrating stress elsewhere. Caloris Basin offers an example of regional interaction between impact processes and tectonics. Caloris is one of the largest impact basins in the solar system, about 1,550 kilometers in diameter. The impact that formed it would have significantly altered local crustal thickness and stress patterns. Subsequent compressional features around Caloris suggest that contraction interacted with pre-existing structures. This interplay shows that Mercury's geological history is not a single event, but a sequence of overlapping processes: impact formation, volcanic resurfacing, internal cooling, global contraction. Each phase left marks on the surface. Today, Mercury appears quiet. There are no active volcanoes, no visible tectonic motion detectable from orbit. But the absence of dramatic change does not mean geological processes have ceased. If contraction is still ongoing, even at an extremely slow rate, new fault activity could occur sporadically. Seismic measurements would provide definitive evidence, but no seismometer has yet operated on Mercury's surface. Future missions, such as the European Space Agency and JAXA's Bepi-Colombo spacecraft, are expected to provide additional data. Improved mapping of gravity and magnetic fields may refine models of internal cooling. Understanding Mercury's contraction also informs broader planetary science. Mars shows signs of ancient tectonic stress, but lacks the same global compressional signature. The Moon exhibits small contraction scarps, indicating that it too has cooled and shrunk slightly. Mercury represents an extreme case, a planet whose internal proportions amplify the effects of cooling. By studying Mercury, scientists gain insight into how rocky planets evolve after formation. Cooling is inevitable. Radioactive heat sources decay. Interiors solidify. The pace and consequences depend on size, composition, and structure. Mercury's story is not about sudden destruction. It is about gradual transformation driven by thermodynamics. Energy radiates into space. Metals crystallize. Volume decreases. Crust fractures. And a small planet slowly changes shape over billions of years. In the next section, we will examine how Mercury's environment near the Sun influences this evolution, exploring the role of solar radiation, tidal forces, and orbital dynamics in shaping the planet's long-term stability. Each of these external factors interacts subtly with the internal processes already described, and together they define the future of Mercury. Mercury does not evolve in isolation. While its internal cooling drives contraction, the planet's proximity to the Sun adds another layer of influence, one that shapes its surface conditions, orbital behavior, and long-term stability. No other rocky planet orbits so close to the Sun. At its nearest point, Mercury approaches within 46 million kilometers. At its farthest, it stretches to about 70 million kilometers. This highly elliptical orbit exposes the planet to intense variations in solar energy. These variations create extreme temperature swings. When Mercury faces the Sun during perihelion, surface temperatures can exceed 430 degrees Celsius. In permanent shadow at the poles, temperatures can fall below minus 170 degrees Celsius. Such thermal contrast has consequences. Every Mercury day, which lasts about 176 Earth days, the surface expands under sunlight and contracts in darkness. Rocks heat, then cool, expand, then shrink. Over millions and billions of cycles, this repeated stress weakens surface material. Thermal fatigue fractures rock. Small cracks propagate slowly. Edges crumble. Slopes become unstable. This process is not directly responsible for global contraction, but it modifies the surface over time, interacting with tectonic features. For example, cliffs created by thrust faults experience daily heating and cooling. The stress from temperature swings can gradually erode their sharp edges, altering their profiles. In addition to temperature, solar radiation plays a powerful role. Mercury's atmosphere, more accurately called an exosphere, is extremely thin. It does not shield the surface from charged particles streaming from the Sun. The solar wind continuously bombards the planet. This constant exposure strips away atoms from the surface in a process known as sputtering. High-energy particles knock atoms loose, allowing them to escape into space. Over time, this contributes to gradual surface alteration. Because Mercury lacks a dense atmosphere, it cannot protect volatile compounds efficiently. Yet MESSENGER detected evidence of volatile elements, including sulfur and possibly even traces of water ice in permanently shadowed craters near the poles. These polar craters never receive direct sunlight due to Mercury's minimal axial tilt, only about 0.03 degrees. As a result, their interiors remain permanently cold. Radar observations and spacecraft measurements confirm deposits of water ice in these regions. This discovery complicates earlier assumptions about Mercury's composition. Despite extreme daytime heat, some regions preserve frozen material for billions of years. The presence of ice does not contradict the planet's contraction, but it demonstrates that Mercury's environment is more diverse than once believed. Now consider tidal forces. Mercury is locked in a 3-to-2 spin-orbit resonance. For every 2 orbits around the Sun, it rotates 3 times. This unusual configuration is the result of gravitational interactions over long timescales. Tidal forces from the Sun exert stress on Mercury's interior. As the planet moves along its elliptical orbit, tidal stress varies slightly. This periodic stress may interact with tectonic faults, though the magnitude is small compared to contraction forces. Still, tidal flexing contributes to the overall stress environment of the crust. Because Mercury's core remains partially liquid, tidal forces can also influence fluid motion within the core. Subtle variations in gravitational pull may affect internal flow patterns, possibly contributing to the asymmetry observed in the magnetic field. Solar radiation also gradually affects Mercury's orbit itself. Over very long timescales, gravitational interactions between planets cause orbital parameters to shift. Mercury's orbit is particularly sensitive due to its proximity to the Sun and its relatively low mass. Simulations of solar system dynamics show that Mercury's orbit can become increasingly eccentric over billions of years, although the probability of catastrophic orbital instability is low in the near future. Long-term models suggest that Mercury's orbit is the most chaotic among the planets. This does not mean Mercury will be ejected soon, but compared to other planets, its path is less stable over extreme timescales. While internal cooling shrinks the planet, gravitational dynamics shape its motion. These two processes, thermal evolution and orbital evolution, operate independently but simultaneously. There is another factor to consider: the Sun itself. The Sun slowly increases in luminosity over time as it converts hydrogen to helium in its core. This gradual brightening means Mercury receives slightly more solar energy as billions of years pass. In the distant future, as the Sun enters its red giant phase, Mercury's fate will likely be sealed. The expanding outer layers of the Sun may engulf the planet entirely, but that event lies billions of years ahead. In the present era, Mercury's transformation is dominated by internal cooling rather than external destruction. Still, solar proximity accelerates certain surface processes. Micrometeoroid impacts occur frequently, due to Mercury's position within the inner solar system. Small impacts continually churn the regolith, exposing fresh material and modifying tectonic features. Because Mercury has no atmosphere to slow incoming debris, even small particles strike the surface at high velocities. Impact gardening mixes surface layers, redistributing material and influencing crater formation rates. Compression and impacts sometimes intersect. A thrust fault can cut through an impact crater. Conversely, a new crater can form on top of a scarp. Each interaction provides scientists with chronological clues. By studying these cross-cutting relationships, researchers reconstruct Mercury's geological timeline in detail. One might ask whether Mercury could ever experience plate tectonics like Earth. The answer appears to be no. Plate tectonics requires sustained mantle convection and a relatively thin, mobile lithosphere. Mercury's mantle is thin, and its lithosphere is thick and rigid. As internal heat decreases further, the lithosphere becomes even more rigid. Instead of developing moving plates, Mercury simply contracts as a whole. This fundamental difference explains why Earth recycles crust while Mercury preserves ancient surfaces. Mercury's oldest terrains date back over 4 billion years. Large portions of the surface have remained largely unchanged, except for impacts and compressional faulting. The lack of atmosphere, erosion, and tectonic recycling preserves a record of early solar system conditions. In this sense, Mercury acts as a geological archive, but it is not completely static. If contraction continues, even at a slow pace, new scarps may still form. Future missions could potentially detect minor seismic activity if instruments sensitive enough were deployed. Until then, scientists rely on orbital measurements to infer ongoing processes. The story of Mercury is not one of dramatic collapse. It is the steady consequence of thermodynamics. A planet forms, it heats, it cools, its metal interior crystallizes, its volume decreases, its crust adjusts. External factors, solar radiation, tidal stress, micrometeoroid impacts, shape the surface environment, but they do not drive the fundamental change. The primary driver remains internal cooling. Mercury's position near the Sun intensifies surface conditions, but does not create contraction. Instead, the planet's unique structure, oversized core, thin mantle, rigid lithosphere, amplifies the effects of cooling in a way unmatched by other rocky worlds. In the next section, we will examine how Mercury compares directly to Earth, Mars, and the Moon, exploring why contraction appears differently on each body and what this comparison reveals about planetary evolution across the inner solar system. By placing Mercury in context, its slow transformation becomes clearer, not as an anomaly, but as one outcome among many possible evolutionary paths for rocky planets. Mercury's slow contraction becomes more meaningful when we compare it to the other rocky worlds in the inner solar system. Each terrestrial planet formed from similar building blocks, rock and metal gathered from the early solar nebula. Yet their evolutionary paths diverge dramatically. The differences are not random. They are governed by size, composition, distance from the Sun, and internal heat. Start with Earth. Earth is larger than Mercury, more than twice its diameter, and far more massive. That size difference changes everything. A larger planet retains heat longer. Its interior cools more slowly because heat must travel a greater distance to escape. Earth's mantle remains convecting today, hot material rises, cooler material sinks, and this circulation drives plate tectonics. Instead of shrinking as a whole, Earth constantly reshapes itself through moving plates. Compression occurs at subduction zones, where plates collide. Extension occurs at mid-ocean ridges, where new crust forms. Stress is redistributed dynamically. Earth is cooling too. All rocky planets cool. But the cooling is buffered by ongoing convection and radioactive heat production. The crust does not globally contract, it is recycled. Mercury, by contrast, lacks this internal circulation. Its mantle is too thin and its lithosphere too thick. Once internal heat declined below a certain threshold, large-scale convection diminished. Without moving plates, stress from contraction accumulated in the crust instead of being redistributed. Now consider Mars. Mars is larger than Mercury, but smaller than Earth. Its internal evolution sits between the two. Early in its history, Mars had active volcanism and possibly some tectonic processes. Massive volcanoes, such as Olympus Mons, formed from mantle plumes. However, Mars cooled faster than Earth. Today, it shows little evidence of active tectonics. Its lithosphere thickened over time. Mars does display some contraction features, wrinkle ridges and minor faulting, but not the extensive global scarps seen on Mercury. Why the difference? Mars has a larger mantle relative to its core. Its internal composition and structure distribute cooling differently. While Mars lost much of its internal heat, its contraction did not produce the same magnitude of compressional stress across the entire crust. Now look at the Moon. The Moon is smaller than Mercury and cooled rapidly after formation. It too shows evidence of contraction. Lunar reconnaissance data revealed small thrust faults, sometimes called Lobate scarps, similar in shape to those on Mercury, but much smaller in scale. The Moon may have shrunk by tens of meters as its interior cooled, far less than Mercury's estimated several kilometers of radius reduction. The difference lies again in composition and core size. The Moon's core is small relative to its total size. Solidification of a small core results in less overall volume reduction. Mercury's unusually large core amplifies contraction effects. Another factor is density. Mercury is extremely dense for its size. Its density is nearly comparable to Earth's, despite being much smaller. This high density reflects its metal-rich interior. Density influences gravitational stress and structural strength. The greater proportion of metal inside Mercury creates a different internal pressure distribution. Compared to Mars or the Moon, when that metal cools and crystallizes, the mechanical response differs accordingly. Venus provides another comparison. Venus is similar in size to Earth, but lacks plate tectonics. Its surface appears relatively young due to widespread volcanic resurfacing in the past. However, Venus does not display the same type of global contraction scarps as Mercury. Venus retains more internal heat because of its size. Additionally, its thick atmosphere traps heat, creating a greenhouse effect that affects surface temperature, but does not directly control deep interior cooling. Venus may experience episodic resurfacing events rather than continuous plate tectonics or steady contraction. Each planet therefore illustrates a different outcome of thermal evolution. Earth, slow cooling with active tectonics. Mars, intermediate cooling with declining activity. Moon, rapid cooling with limited contraction. Venus, retained heat with resurfacing episodes. Mercury, rapid cooling combined with an oversized core, producing global compression. These comparisons reveal that contraction is not unique to Mercury. It is a universal consequence of planetary cooling. What makes Mercury special is the magnitude and clarity of its response. Mercury acts almost like a laboratory model of core-driven contraction. Because its mantle is thin and inactive, the signal from the core passes directly to the surface. There is little internal buffering. This makes Mercury valuable scientifically. By studying Mercury, scientists refine models of how metallic cores solidify over time. These models apply not only to planets, but also to large asteroids and exoplanets. In fact, some exoplanets discovered in other star systems appear to be iron-rich and dense, similar to Mercury. Observing Mercury provides a nearby example of how such bodies might evolve. Another comparison involves magnetic fields. Earth's magnetic field is strong and globally protective. It arises from convection in the liquid outer core. Mars once had a magnetic field but lost it as its core cooled and solidified. Mercury still has a magnetic field, though weak. Its persistence suggests that part of its core remains molten despite significant cooling. This intermediate state, partially solidified but not fully, creates the ongoing contraction we observe. Eventually, Mercury's core may solidify completely. If that happens, contraction will slow and possibly cease. The magnetic field would likely disappear, as happened on Mars. Without a magnetic field, solar wind erosion could intensify slightly, though Mercury's exosphere is already extremely thin. The timeline for complete solidification is uncertain. It depends on heat flow, composition, and the amount of sulfur or other light elements in the core. But based on current models, Mercury still has billions of years before reaching that state. In the meantime, contraction continues. Understanding contraction also improves our knowledge of planetary strength. Rocks under compression behave differently depending on temperature and composition. By measuring scarp geometry and estimating stress levels, scientists infer mechanical properties of Mercury's crust. This informs material science models relevant not only to planets, but also to engineering under extreme conditions. Even more broadly, Mercury challenges earlier assumptions that small rocky planets become entirely geologically dead early in their history. Instead, Mercury demonstrates that even a small planet can remain internally dynamic for billions of years, though in a subtle way. Not with volcanoes erupting, not with plates colliding, but with slow structural adjustment. Comparison also highlights a key principle. Planetary evolution is not linear. It is determined by initial conditions. Two planets may form from similar materials, yet slight differences in mass, distance from the Sun, and impact history produce radically different outcomes. Mercury's potential giant impact early in its history may have shaped its entire destiny. If its mantle had not been stripped, if its core were proportionally smaller, contraction might have been less dramatic. Its surface might look more like Mars or the Moon. Instead, its iron-rich interior dictates a different path. Looking outward, we see that no two rocky worlds are identical, but they all share one truth. They cool. Internal heat dissipates into space. Metal crystallizes. Mantles solidify. Crusts respond. Mercury simply reveals this process in a particularly visible way. In the next section, we will explore what Mercury's continued contraction means for its long-term future. Not billions of years from now when the Sun expands, but within the time frame of planetary cooling itself. We will examine whether the planet could fracture further, how its surface might evolve, and what eventual equilibrium might look like once contraction slows. Each stage of cooling leaves its mark, and Mercury is still writing that record. If Mercury's contraction is driven by the gradual cooling and solidification of its core, then the natural question is what happens next. A planet cannot shrink indefinitely. At some point, the rate of internal heat loss slows, crystallization stabilizes, and the mechanical adjustments at the surface diminish. To understand Mercury's future, we need to examine how thermal evolution works over extremely long timescales. Every rocky planet begins hot. Heat comes from several sources: the energy of accretion during formation, radioactive decay of elements such as uranium and thorium, and differentiation as heavy materials sink towards the center. Over time, those heat sources decline. Radioactive isotopes decay. Impacts become less frequent. Internal convection weakens. The cooling curve is not linear. Early in a planet's life, heat loss is rapid because temperature differences between interior and space are large. As the planet cools, that temperature gradient decreases. The rate of heat loss slows. Mercury has already passed through the most intense phase of cooling. The massive lava plains seen today likely formed within the first billion years of its history. That was the period when internal heat was sufficient to drive widespread volcanism. Since then, heat production has decreased dramatically. Current models suggest that Mercury's interior temperature continues to decline, but much more slowly than in its earliest history. As the core solidifies further, the inner core grows. The remaining liquid outer core shrinks. The overall contraction rate decreases over time because the volume of molten material available to crystallize becomes smaller. This means that the most dramatic phase of shrinkage has already occurred. However, even a small amount of ongoing crystallization can generate stress. If the contraction rate today is measured in millimeters per year or less, it would still accumulate over millions of years. Geological processes operate on timescales far beyond human experience. The key question is whether Mercury's lithosphere can continue to absorb this stress without catastrophic failure. Based on existing scarp distribution, the crust has accommodated contraction efficiently through thrust faulting. New faults may form where stress concentrates, while older faults may experience minor reactivation. There is no evidence of large-scale crustal collapse or instability. Instead, contraction appears to proceed in small increments. If Mercury's core were to solidify completely, contraction would largely cease. The crust would stabilize in its final compressed state. Scarps would remain as permanent features. Another consequence of full core solidification would be the disappearance of Mercury's magnetic field. A planetary magnetic field requires fluid motion in a conductive outer core. Once the core becomes entirely solid, convection stops and the dynamo effect ends. Mars provides a precedent. It once possessed a global magnetic field, as recorded in magnetized crustal rocks. But as its core cooled and solidified, the dynamo shut down. If Mercury loses its magnetic field in the distant future, the solar wind will interact more directly with its surface. However, because Mercury's exosphere is already extremely thin, the practical difference may be modest. The surface would continue to experience sputtering and particle bombardment, much as it does today. Thermal cycling would continue as long as Mercury orbits the Sun. The larger-scale future of Mercury is tied to solar evolution. In roughly 5 billion years, the Sun will exhaust hydrogen in its core and expand into a red giant. During that phase, the Sun's outer layers may extend outward beyond Mercury's current orbit. Whether Mercury will be engulfed or survive as a remnant core depends on complex interactions involving mass loss from the Sun and orbital expansion. Most models predict that Mercury will not survive. But that scenario lies billions of years ahead. Within the time frame of internal cooling alone, Mercury's evolution is more gradual. There is also the matter of orbital stability. Mercury's orbit is influenced by gravitational interactions with Venus, Earth, and Jupiter. Long-term simulations indicate that Mercury's orbital eccentricity can vary chaotically over hundreds of millions of years. Although the probability is small, some models suggest that over extremely long timescales, Mercury could experience orbital destabilization, potentially colliding with another planet or being ejected. Such events are statistically rare within the Sun's remaining lifetime. In the absence of catastrophic orbital changes, Mercury's geological story is defined by steady cooling. One area of ongoing research involves estimating the exact rate of present-day contraction. Direct measurement is challenging. Without seismometers or surface instruments, scientists rely on crater counting and structural analysis. Future missions may improve resolution and detect subtle changes in surface topography. The European-Japanese Bepi-Colombo mission, currently en route to Mercury, is designed to study the planet's magnetic field, gravity field, and internal structure in greater detail. Refined data may clarify whether contraction is still active or has slowed significantly. Another open question concerns how contraction affects Mercury's stress distribution over time. As new faults form, they alter how stress propagates through the crust. Regions that have already fractured may accommodate additional compression more easily than intact regions. This feedback can influence where future scarps might appear. Computer models of planetary contraction simulate how a spherical shell responds to volume reduction. These models show that stress may concentrate preferentially at certain latitudes depending on rotational and tidal effects. On Mercury, scarps are found globally, but subtle distribution patterns may reveal underlying structural differences. In addition, compositional variations within the crust could affect mechanical behavior. Regions with different mineral content may respond differently to compression. Understanding these variations requires high-resolution spectroscopic mapping. Looking even further ahead, one might ask whether Mercury could ever reheat internally. The answer is effectively no. Without new sources of internal energy, cooling is irreversible. There are no mechanisms for significant reheating once radioactive decay declines and accretional heat dissipates. Mercury will not regain volcanic activity in any substantial way. It will continue to lose heat, albeit slowly. In that sense, Mercury is not destroying itself in a dramatic collapse. It is settling. The term destroying describes the visible fracturing and compressional reshaping, but physically, the process is a natural transition toward thermal equilibrium. The planet is is moving toward a stable, solid interior configuration. This process is fundamental to rocky worlds. Planets form hot and active. Over billions of years, they cool and become quieter. Earth remains active because of its size and internal structure. Mercury, smaller and metal-dominated, moves more quickly toward rigidity. The cliffs and faults visible today represent accumulated history, a record of internal change written across the surface. Eventually, that record will cease to grow. The crust will reach a state where contraction is minimal. Scarps will erode slowly under micrometeoroid bombardment and thermal fatigue. Impact craters will accumulate. Mercury will appear even more ancient than it does today. Yet even then, the scars of contraction will remain. They are not superficial marks. They are structural. They reflect changes deep within the planet's core. In the next section, we will examine how scientists model Mercury's interior mathematically, exploring heat flow equations, crystallization physics, and mechanical stress calculations that support the contraction theory. Behind every observed cliff lies a quantitative framework. Understanding that framework completes the picture of how and why Mercury slowly reshapes itself. To understand Mercury's contraction with precision, scientists rely on mathematical models that simulate how heat moves through a planet, how metal crystallizes under pressure, and how stress accumulates in a rigid shell. These models are not speculative. They are grounded in physics, thermodynamics, materials science, and gravitational mechanics. At the center of the problem is heat flow. A planet cools because its internal temperature is higher than the temperature of space. Heat naturally moves from hot regions to cold ones. In a rocky body like Mercury, heat transfer occurs primarily through conduction once convection slows. Conduction is a relatively slow process. It depends on the thermal conductivity of materials and the temperature gradient between interior and surface. The rate of heat loss can be described using Fourier's law, which relates heat flux to the temperature gradient and the conductivity of the material. In Mercury's case, the thin mantle and thick lithosphere influence how heat escapes. The mantle once convected when temperatures were higher. As it cooled and stiffened, convection diminished. Heat then had to pass through the lithosphere, mainly by conduction. This shift changes the cooling curve. Early in Mercury's history, convective heat loss was more efficient. Later, conductive cooling dominated, slowing the rate of temperature decline. Inside the core, the situation is different. The core is metallic and conductive. As it cools, crystallization begins when temperatures drop below the liquidus, the temperature at which iron alloys solidify under pressure. When crystallization occurs, two important things happen. First, latent heat is released. When liquid metal solidifies, it releases energy. This temporarily slows cooling. Second, volume changes. Solid iron occupies slightly less volume than liquid iron under similar pressure conditions. The precise contraction depends on composition and pressure, but the effect is measurable. To model this process, scientists calculate how the inner core grows over time. The growth rate depends on how quickly heat escapes and how quickly the liquid outer core loses thermal energy. As the inner core expands outward, the outer core becomes thinner. The total planetary radius decreases slightly. Now consider the mechanical response. Mercury's crust behaves approximately as a spherical elastic shell under compression. In engineering terms, when a spherical shell shrinks internally, compressive stress builds tangentially across its surface. If the compressive stress exceeds the yield strength of rock, failure occurs. The orientation and distribution of faults depend on stress direction and lithospheric thickness. Mathematical stress models predict that contraction produces thrust faults, oriented in various directions, but globally distributed. That matches observations of lobate scarps on Mercury. The magnitude of stress can be estimated. If Mercury's radius decreased by several kilometers over billions of years, the average horizontal strain in the crust would be on the order of a few tenths of a percent. That may sound small, but rock is brittle. Even a fraction of a percent strain can generate fracturing at planetary scale. Another important parameter is elastic thickness, the thickness of the lithosphere that behaves rigidly under stress. Estimates based on gravity and topography data suggest that Mercury's elastic lithosphere may be more than 100 kilometers thick in some regions. A thick lithosphere can sustain large stresses before failing. But when it fails, the resulting faults are substantial. In addition to purely thermal contraction, scientists incorporate compositional models. Mercury's core likely contains sulfur and possibly silicon. These elements affect crystallization temperature and density. As the core cools, the composition of remaining liquid changes. Light elements may concentrate in the liquid phase, altering buoyancy and convection patterns. This can influence magnetic field generation and heat transport. Magnetohydrodynamic models simulate how fluid motion in the outer core generates Mercury's magnetic field. By matching observed field strength and asymmetry, researchers constrain how much liquid remains and how fast it cools. All these models converge on a consistent conclusion. Mercury is still cooling, and partial solidification continues. There is also the matter of mantle rheology, how the mantle deforms under stress. Rheology describes how materials flow over time. At high temperatures, rock can deform ductilely. At lower temperatures, it fractures. Mercury's mantle has likely transitioned from partially ductile to mostly rigid over time. That transition affects how contraction stress transfers to the crust. Early in its history, some contraction may have been absorbed by ductile flow at depth. As cooling progressed, the mantle stiffened, increasing the proportion of stress reaching the brittle crust. This shift could explain why some scarps appear younger than expected. To test these ideas, scientists run computer simulations varying parameters such as core size, sulfur content, initial temperature, and lithosphere thickness. By adjusting these variables, they determine which combinations reproduce observed scarp distribution and estimated shrinkage. Another modeling tool involves moment of inertia calculations. Mercury's mass distribution affects its rotational behavior. By measuring librations and gravity harmonics, scientists calculate the ratio of core to mantle mass. These values feed back into thermal models, refining predictions of contraction. One subtle aspect concerns how contraction stress evolves spatially. Because Mercury rotates and experiences solar tides, stress may not be perfectly uniform. Some models predict slightly higher compression near the equator compared to the poles, though observations show global scarp distribution. Refining these spatial predictions requires higher resolution data. The reliability of contraction theory is strengthened by consistency across independent methods. Gravity field mapping confirms a massive core. Rotational measurements confirm a liquid outer core. Magnetic data confirm ongoing fluid motion. Topography mapping reveals global thrust faults. Crater dating suggests contraction persisted over long periods. Each dataset supports the same narrative. Planetary science relies on cross-validation. No single observation proves a theory. Instead, convergence of evidence builds confidence. Mercury's contraction model is one of the most robust examples of this approach. Still, uncertainties remain. The exact rate of present-day contraction is unknown. The precise composition of the core is not directly measured. The thickness of the mantle varies regionally. Future missions may refine these uncertainties. From a broader perspective, Mercury demonstrates the importance of internal energy budgets in planetary evolution. A planet's fate depends largely on how much heat it starts with, how quickly it loses that heat, and how its internal layers respond mechanically. Size matters, composition matters, distance from the Sun matters. Mercury's small size accelerates cooling. Its large core amplifies contraction. Its thin mantle transmits stress directly to the crust. These three factors together explain why Mercury's surface records such extensive compressional tectonics. Mathematical models do not simply describe this process. They quantify it. They allow scientists to estimate how much Mercury has shrunk when contraction was most active, and how it may continue in the future. In the next section, we will examine how observational evidence from spacecraft missions, particularly Mariner 10, Messenger, and Bepi Colombo, transformed our understanding of Mercury from a cratered relic to a dynamically evolving planet. Because without spacecraft data, contraction would have remained a hypothesis. It is orbital exploration that revealed the cliffs, measured the magnetic field, and provided the evidence needed to confirm that Mercury is, in fact, slowly reshaping itself. For much of the 20th century, Mercury was a mystery defined by distance. From Earth, it is difficult to observe clearly. It never strays far from the Sun in the sky. Telescopes on Earth can glimpse only partial phases, blurred by atmospheric distortion and limited viewing windows at dawn or dusk. Before spacecraft exploration, knowledge of Mercury was fragmentary. Astronomers could estimate its size, mass, and orbit. They knew it was dense. They knew it lacked a substantial atmosphere, but its surface and interior remained largely unknown. That changed in 1974. NASA's Mariner 10 spacecraft became the first probe to visit Mercury. It flew past the planet 3 times between 1974 and 1975. Mariner 10 mapped about 45% of Mercury's surface. What it revealed was surprising. The surface looked heavily cratered, resembling the Moon. There were vast impact basins, long ridges, and rugged terrain. One feature in particular stood out: long curved cliffs cutting across craters and plains. These were the first glimpses of what would later be identified as Lobat scarps. At the time, scientists suspected these features might indicate contraction. but the limited coverage prevented global conclusions. Without a complete map, it was impossible to determine whether these structures were local anomalies or global tectonic patterns. For decades, Mercury remained unexplored. Then, in 2004, NASA launched MESSENGER, Mercury surface, space environment, geochemistry, and ranging. MESSENGER entered orbit around Mercury in 2011 and remained there until 2015, when it intentionally impacted the surface after exhausting its fuel. During its 4 years in orbit, MESSENGER transformed our understanding of the planet. It mapped nearly 100% of Mercury's surface in high resolution. It measured gravity variations, magnetic fields, elemental composition, and topography. The data were precise enough to quantify contraction. High-resolution images revealed thousands of low-bat scarps distributed across the entire planet. Some were small, only a few kilometers long. Others extended hundreds of kilometers. Their orientation varied, but their mechanical nature was consistent. Compressional thrust faults. Using topographic measurements, scientists calculated how much vertical displacement occurred along these faults. By summing these displacements globally, they estimated the total radial shrinkage required to produce them. Initial estimates suggested about 1 to 2 kilometers of radius reduction. Later refinements using improved data and more complete coverage increased that estimate to roughly 5 to 7 kilometers. That magnitude confirmed that Mercury experienced significant global contraction. MESSENGER also provided gravity field data that refined models of Mercury's interior. By tracking the spacecraft's motion precisely, scientists mapped variations in gravitational pull across the planet. These measurements allowed estimation of core size and mantle thickness. At the same time, MESSENGER's magnetometer measured Mercury's magnetic field in detail. It confirmed that the field is weak but global, and that it is offset northward relative to the planet's center. This asymmetry suggests uneven core dynamics. MESSENGER also detected volatile elements such as sulfur and potassium in surface rocks. This challenged earlier assumptions that Mercury was extremely depleted in volatiles due to its proximity to the Sun. The presence of these elements influenced models of core composition and crystallization behavior. One of the most important discoveries involved the relative age of scarps. By analyzing crater density on and around thrust faults, scientists determined that some scarps cut across relatively young terrain. This suggested that contraction did not cease early in Mercury's history, but continued for billions of years. MESSENGER's altimeter created detailed elevation maps, allowing researchers to measure scarp heights accurately. Some scarps exceeded 1 kilometer in relief. These were not minor wrinkles, but major tectonic structures. The spacecraft also discovered hollows, shallow depressions associated with volatile loss. While not directly tied to contraction, hollows added complexity to Mercury's geological story. After MESSENGER's mission ended, attention turned to the next generation of exploration. The European Space Agency and the Japan Aerospace Exploration Agency launched Bepi Colombo in 2018. The spacecraft is scheduled to enter orbit around Mercury in the mid-2000s. Bepi Colombo carries advanced instruments designed to refine measurements of gravity, magnetic field, and surface composition. With improved sensitivity and extended orbital coverage, it aims to answer remaining questions. How thick is Mercury's lithosphere in different regions? How much liquid remains in the outer core? Is contraction still occurring today? What explains the magnetic field asymmetry? High-precision gravity mapping will improve estimates of internal layering. Magnetometer data from multiple spacecraft components will clarify dynamo behavior. In addition, Bepi-Colombo's imaging systems will produce higher resolution maps of tectonic features, potentially identifying smaller or younger scarps missed by MESSENGER. Spacecraft observations also provide insight into Mercury's exosphere and interaction with the solar wind. Instruments measure how charged particles strike the surface and how atoms are ejected into space. These data help model long-term surface evolution under solar radiation. One subtle but important advancement in planetary science is the integration of spacecraft data with laboratory experiments. By recreating high-pressure conditions in labs, scientists study how iron-sulfur alloys behave during crystallization. These results feed back into core solidification models, improving predictions of contraction rates. Space missions thus connect observational data with physical theory. Without Mariner 10, contraction might have remained speculative. Without MESSENGER, it would have lacked quantitative confirmation. Without Bepi-Colombo, key uncertainties might persist. Mercury illustrates how incremental exploration builds scientific understanding over decades. Each mission adds resolution, not just in images, but in theory. As data accumulate, contraction transitions from hypothesis to measured phenomenon. The cliffs on Mercury's surface are no longer mysterious ridges. They are expressions of internal thermodynamics. The planet's magnetic field is no longer puzzling. It is evidence of ongoing core crystallization. Mercury is no longer viewed as a static relic of early solar system history. It is recognized as a planet that continues to evolve, slowly, predictably, according to physical laws. In the next section, we will examine how Mercury's contraction influences our understanding of planetary habitability and exoplanets, exploring what its evolution tells us about rocky worlds beyond our solar system. Because while Mercury itself is inhospitable, its physics applies universally, and its slow transformation provides a template for understanding other metal-rich planets orbiting distant stars. Mercury's slow contraction is not only a local geological story, it provides a framework for understanding how rocky planets evolve everywhere, including worlds beyond our solar system. While Mercury itself is inhospitable, the physics shaping it applies broadly to any metal-rich terrestrial planet. Over the past 3 decades, astronomers have discovered thousands of exoplanets orbiting other stars. Among them are many rocky planets that are larger than Earth, smaller than Neptune, and often extremely close to their parent stars. Some of these exoplanets have unusually high densities, suggesting large metallic cores relative to their size. In other words, there may be super-Mercuries in other star systems. Understanding Mercury helps scientists model how such planets cool, how long their magnetic fields might last, and whether their surfaces remain tectonically active. Thermal evolution is universal. A rocky planet forms hot from accretion and radioactive decay. It begins cooling immediately. The cooling rate depends on mass, composition, and distance from its star. Mass plays a critical role. Larger planets retain heat longer because they have lower surface area to volume ratios. Smaller planets lose heat faster. Mercury, being small, cools rapidly. But because it is metal-rich, the contraction effects are amplified. If an exoplanet forms with a disproportionately large iron core, similar processes would occur. Core solidification would drive contraction. A thick, rigid lithosphere would fracture under compressive stress. The resulting surface features might resemble those observed on Mercury: global thrust faults and scarps. Magnetic fields are another key factor. A magnetic field requires a liquid outer core and sustained convection. Once the core solidifies, the dynamo effect ceases. Without a magnetic field, a planet's atmosphere becomes vulnerable to stellar wind stripping. Mercury's magnetic field is weak but present, indicating partial core liquid. Mars lost its global magnetic field early in its history. Earth maintains a strong one because of its size and active convection. By studying Mercury's thermal timeline, scientists estimate how long a metal-rich planet of similar size might sustain a dynamo. For exoplanets orbiting close to their stars, stellar radiation and tidal forces complicate matters further. Many rocky exoplanets orbit much closer to their stars than Mercury does to the Sun. In such cases, tidal heating could influence internal temperature. Tidal forces can generate frictional heat inside the planet, potentially prolonging internal activity. Mercury experiences tidal forces from the Sun, but they are not strong enough to dominate its internal energy budget. In contrast, exoplanets in tight orbits may experience intense tidal heating, which could partially offset cooling. This introduces a new variable in thermal evolution models. Metal-rich exoplanets might cool and contract similarly to Mercury, but if tidal heating is significant, the cooling timeline could be extended. Composition also matters. Mercury's core likely contains sulfur, lowering its melting point and allowing partial liquidity to persist. Exoplanets with different light element content may crystallize differently. If an exoplanet's core lacks light elements, it might solidify faster, ending magnetic activity earlier. These differences influence planetary atmospheres and potential habitability. Habitability requires more than just liquid water. It often depends on long-term geological stability and magnetic shielding. Mercury demonstrates what happens when a small rocky planet loses most of its internal heat. It becomes tectonically inactive, except for slow contraction. Its magnetic field weakens. Its surface becomes dominated by impacts and thermal fatigue rather than volcanic resurfacing. For an exoplanet of similar size in the habitable zone of a star, rapid cooling might limit geological recycling processes that regulate climate. Earth's long-term climate stability is linked to plate tectonics and volcanic outgassing, which cycle carbon between interior and atmosphere. Mercury lacks such recycling. In that sense, Mercury represents one end member of terrestrial planetary evolution, a small, cooling world with limited internal dynamism. By contrast, Earth represents a larger, still active world. Mars lies somewhere in between, having cooled enough to lose its magnetic field, but still preserving volcanic provinces. Comparative planetology allows scientists to map these trajectories across parameter space. Mercury provides the metal-rich, contraction-dominated scenario. Another area of relevance is planetary differentiation. Mercury's large core may have formed through early giant impacts or preferential metal accumulation near the Sun. If similar processes occur elsewhere, planets with extreme core-to-mantle ratios may be common. Observational data from exoplanets often include mass and radius measurements. From these two quantities, scientists estimate bulk density. High density suggests a large metallic component. For example, some exoplanets have densities exceeding Earth's despite similar sizes. These worlds may resemble Mercury internally. Understanding Mercury's cooling and contraction informs predictions about surface tectonics on such planets. Will they develop plate tectonics, or will they contract globally? Models suggest that plate tectonics require specific conditions: sufficient internal heat, appropriate lithospheric thickness, and water to weaken rock. Mercury lacks these conditions. If a supermercury exoplanet lacks water and has a thick lithosphere, it may also avoid plate tectonics and instead exhibit contractional tectonics. Another insight from Mercury involves surface preservation. Because Mercury lacks atmosphere and erosion, ancient features remain intact for billions of years. On exoplanets without atmospheres, contraction features could persist similarly. However, detecting such features directly on exoplanets is currently beyond technological capability. Instead, scientists infer internal processes from indirect measurements such as magnetic signatures, density, and orbital characteristics. Mercury also provides a cautionary example. Early in planetary science, Mercury was assumed to be geologically dead after its early history. Only detailed spacecraft mapping revealed ongoing contraction. Similarly, exoplanets once assumed inactive may still undergo slow internal change. Planetary evolution is subtle. Even small bodies can remain internally dynamic long after formation. Mercury teaches that cooling does not mean complete inactivity. It means transformation under different rules. In addition, studying Mercury refines equations governing planetary cooling timescales. These equations depend on thermal conductivity, heat capacity, latent heat of crystallization, and initial temperature. By calibrating models against Mercury's observed contraction and magnetic field persistence, scientists improve predictions for other rocky worlds. In the coming decades, telescopes such as the James Webb Space Telescope and future missions will refine exoplanet characterization. Although they cannot image surface cliffs, they can detect atmospheric composition and magnetic field signatures indirectly. If a rocky exoplanet lacks atmospheric shielding and magnetic protection, it may resemble Mercury in certain respects. Ultimately, Mercury expands our understanding of planetary diversity. It shows that rocky planets do not all follow Earth's path. Some cool quickly, contract globally, and become structurally rigid. Others retain heat and remain tectonically active. Still others occupy intermediate states. In the next section, we will explore what Mercury's contraction means philosophically for planetary evolution, examining how the concept of destruction differs from dramatic collapse and instead reflects the natural thermodynamic aging of worlds. Mercury is not breaking apart violently. It is reaching equilibrium, and that quiet transformation may be more fundamental than any explosive event. When we describe Mercury as slowly destroying itself, the phrase can sound dramatic. It suggests collapse, instability, or imminent failure. But in planetary terms, Destruction does not always mean violence. More often, it means transformation driven by energy loss. Mercury is not tearing itself apart explosively. It is adjusting to thermodynamic reality. All planets begin with excess energy. That energy must go somewhere. It radiates into space. Cooling is inevitable. The physics governing Mercury's evolution is the same physics that governs every rocky world. The difference lies in scale and proportion. A small planet loses heat faster. A planet with a large metallic core undergoes more contraction during solidification. A planet with a rigid lithosphere fractures rather than flows. Mercury combines all three factors. From a thermodynamic perspective, the planet is moving toward equilibrium, a state in which its interior temperature gradient stabilizes and structural change slows dramatically. This process is not unique to planets. Stars evolve toward equilibrium states until fuel runs out. Asteroids cool and solidify. Even large moons shrink slightly as internal heat dissipates. Mercury's visible cliffs are a direct consequence of this universal law. Systems move from high-energy states toward lower-energy stability. The idea of planetary aging is often overlooked because human timescales are so short. 1 million years seems enormous in human history. In planetary history, it is brief. Mercury's contraction unfolded over billions of years. The cliffs we see today represent accumulated stress from immense spans of time. If contraction continues, it likely does so at a rate too small to detect easily without highly sensitive instruments. This raises an important conceptual point. Geological activity does not require speed. A process can be active yet nearly imperceptible. Mercury's interior still evolves, but slowly. The philosophical shift comes when we understand that planetary death is not an event. It is a gradient. There is no single moment when Mercury became inactive. Instead, activity declined gradually. Volcanism waned. Convection slowed. Contraction replaced expansion. Even today, the planet may experience small tectonic adjustments. Over time, the lithosphere thickens further as cooling continues. A thicker lithosphere means greater rigidity. Greater rigidity means less deformation. Eventually, the crust will reach a point where additional contraction produces minimal new fracturing. At that stage, Mercury will have largely completed its internal adjustment. The surface will continue to record impacts from micrometeoroids and larger bodies, but internally driven tectonics will fade. From an energy standpoint, the planet will approach a steady thermal state. This concept applies across the solar system. The Moon reached such a state earlier due to its small size and small core. Mars reached it later, though it may still harbor residual localized heat. Earth remains far from it because of its size and active convection. Mercury sits between. It is older in thermal terms than Earth, but younger than the Moon in terms of complete interior solidification. Another perspective comes from materials science. Rock under compression accumulates strain energy. When failure occurs along a fault, that energy is released. On Earth, this release can be sudden and violent. Earthquakes. On Mercury, without liquid water and plate boundaries, stress release is less dynamic, but mechanical principles remain the same. If contraction continues, small quakes may occur sporadically. The absence of atmosphere and hydrosphere means that surface modification is minimal. What breaks remains broken. Over immense timescales, micrometeoroid impacts gradually soften edges of scarps. Thermal cycling fractures rock faces. Dust accumulates. But the fundamental structural geometry persists. When we say Mercury is destroying itself, we are describing structural change driven by internal cooling. Yet destruction implies instability. In reality, the planet is becoming more stable. As the core solidifies and the temperature gradient decreases, internal energy diminishes. There is less potential for change. Stability increases. From a systems perspective, Mercury is reducing its complexity. Early in its history, it had molten layers, widespread volcanism, dynamic magnetic activity. Now it has a partially liquid core and a rigid shell. Eventually, it may have a fully solid core and minimal internal motion. Complexity gives way to simplicity. In planetary science, this transition is common. What makes Mercury compelling is how clearly this progression is recorded. The cliffs are not symbolic. They are measurable evidence of volume reduction. The magnetic field is not theoretical. It is directly observed. The gravity data confirm mass distribution. Each piece fits into a coherent framework. There is also a broader lesson in scale. When viewed from space, Mercury appears unchanged over human history. No visible alterations occur year to year, but change does not require visibility on short timescales. Over billions of years, the planet's radius decreased by kilometers. Over billions more, further subtle change will occur. The difference between dramatic and gradual processes often shapes perception more than reality. Supernovae and asteroid impacts capture imagination because they are sudden. Contraction does not. Yet contraction reshapes entire worlds. If we compare Mercury to Earth's own future, the pattern becomes clearer. Earth will cool too. Plate tectonics will eventually cease. The core will solidify. The magnetic field will fade. These changes will take billions of years, but they are inevitable. Mercury simply reached this stage sooner. In that sense, Mercury is not an anomaly. It is an accelerated version of a universal path. Understanding Mercury helps us place Earth within a longer timeline. It reminds us that geological activity is finite. Internal heat is not permanent. The difference between active and inactive worlds lies in mass, composition, and time. In the next section, we will examine how Mercury's future may intersect with external cosmic events, including solar evolution and long-term orbital dynamics, completing the picture of its ultimate fate. Because internal cooling is only part of the story. The Sun itself is changing, and no planet, no matter how stable internally, escapes stellar evolution. Internal cooling explains Mercury's present condition, but the planet's long-term fate cannot be understood without considering the evolution of the Sun itself. Mercury orbits closer to the Sun than any other planet. Its entire existence is defined by that proximity. The same gravitational force that keeps it bound will ultimately determine its end. The Sun is not static. Like all stars, it evolves. At present, the Sun is a main sequence star, fusing hydrogen into helium in its core. This phase has lasted about 4.6 billion years and will continue for roughly another 5 billion. During this period, the Sun gradually increases in luminosity. Stellar models show that a star like the Sun brightens slowly as helium accumulates in its core. Over billions of years, this increasing brightness affects the thermal environment of inner planets. For Mercury, the consequences are incremental. rather than dramatic in the near term. The planet already experiences extreme temperatures due to its lack of atmosphere and close orbit. A gradual increase in solar output slightly intensifies surface heating, but does not fundamentally alter its geological evolution. However, the future beyond the main sequence is transformative. When hydrogen in the Sun's core becomes depleted, nuclear fusion will shift outward into a shell surrounding the core. The core will contract under gravity, heating up, while the outer layers expand. The Sun will enter its red giant phase. During this stage, the Sun's radius will increase dramatically, potentially extending outward beyond Mercury's present orbit. Precise modeling of orbital expansion and stellar mass loss complicates predictions. As the Sun evolves, it will lose mass through stellar winds. Reduced solar mass weakens gravitational binding, allowing planetary orbits to expand outward. The question is whether orbital expansion will outpace solar expansion. Most simulations indicate that Mercury is unlikely to survive this phase intact. Even if its orbit expands slightly due to mass loss, tidal interactions with the Sun's extended outer envelope will likely drag it inward. Mercury may be engulfed entirely. Long before that happens, though, solar evolution will alter Mercury's environment. As the Sun brightens significantly, surface temperatures will rise even further. Any remaining volatile compounds at Mercury's poles, including water ice deposits, will likely sublimate long before the red giant stage. The exosphere will continue to be shaped by solar radiation and particle flux. Internal contraction will have largely stabilized by then. By the time the Sun leaves the main sequence, Mercury's core may already be nearly or completely solid. The magnetic field, if still present, may weaken substantially. Orbital dynamics also play a role. Mercury's orbit is influenced not only by the Sun, but by gravitational interactions with other planets, especially Venus and Jupiter. Numerical simulations of solar system stability over billions of years revealed that Mercury's orbit is the most chaotic among the major planets. Small perturbations can accumulate, leading to variations in eccentricity and inclination, while catastrophic outcomes, such as collisions with Venus or Earth, are statistically unlikely in the near future. Long-term projections suggest that Mercury's orbital stability is less robust than that of other planets. Chaos in orbital mechanics does not mean unpredictability in the short term, but it means that small uncertainties amplify over vast timescales. Even without red giant expansion, Mercury's distant future contains elements of uncertainty. Yet compared to stellar evolution, orbital chaos remains secondary. If engulfment occurs during the red giant phase, Mercury's rocky body would experience extreme heating. Its surface would melt. Its metallic core might vaporize or mix into the Sun's outer layers. In that scenario, Mercury would cease to exist as a distinct planetary body. This is not unique to Mercury. Inner planets in many star systems likely face similar fates as their stars evolve. But before that distant future arrives, Mercury's internal story will have reached its natural conclusion. The planet will have cooled almost completely. Its structural adjustments will have ended. It will have become a rigid metallic rock sphere orbiting a star that itself is aging. The concept of planetary lifespan becomes clearer when viewed alongside stellar lifespan. Planets do not exist independently of their stars. Their evolution is intertwined. Mercury's internal contraction is one chapter. Solar expansion is another. On human timescales, these processes are beyond perception, yet they are governed by measurable physical laws. Stellar models calculate fusion rates, mass loss, and expansion phases with high accuracy. Planetary thermal models estimate cooling curves and core solidification timelines. Together, these models create a coherent long-term picture. There is also a broader implication. The survival of rocky planets in other star systems depends not only on their own internal evolution, but on the life cycle of their stars. A planet may maintain geological stability for billions of years, only to be destroyed when its star evolves. Mercury's proximity to the Sun makes it especially vulnerable. Planets farther out, like Earth, will experience different interactions during the Sun's red giant phase. But even Earth's long-term survival is uncertain. Mercury, being closest, will likely be the first to confront stellar transformation directly. Thus, when we describe Mercury as slowly destroying itself, we must recognize that internal contraction is only one aspect of its finite lifespan. The deeper truth is that planetary existence is temporary. From formation in a protoplanetary disk to eventual destruction or transformation, each planet follows a path shaped by mass, composition, and stellar evolution. Mercury's path is relatively clear. It formed metal-rich. It cooled rapidly. It contracted globally. It preserved its tectonic scars. It will stabilize thermally. And billions of years later, it will likely be consumed as the Sun expands. In the next and final section, we will synthesize these elements: internal thermodynamics, surface geology, comparative planetology, and stellar evolution, into a unified understanding of Mercury's place in the solar system. Because Mercury is not merely a shrinking planet, it is a case study in planetary aging, and through it, we see how worlds change, endure, and eventually disappear. Mercury does not collapse in flames. It does not fracture into fragments. It does not explode. Its story is quieter than that. To understand its fate is to understand the slow mathematics of energy. Every planet begins in excess. Excess heat, excess motion, excess instability. Over time, those excesses fade. Energy radiates away. Motion slows. Internal gradients flatten. What remains is structure hardened by cooling. Mercury is simply further along that path than Earth. Its core once churned more vigorously. Its mantle once convected more freely. Its surface once reshaped itself through volcanic eruptions and tectonic shifts. Today, most of that dynamism has diminished. The lithosphere is thick. The mantle is largely static. The core, though still partially liquid, trends toward solidification. Nothing dramatic signals this transformation. No sudden moment marks the end of activity. Instead, the planet settles incrementally, imperceptibly, into a more stable configuration. That stability is not lifelessness. It is thermodynamic equilibrium. When we say Mercury is destroying itself, what we truly mean is that it is redistributing internal stress accumulated during cooling. The planet shrinks because its metallic core crystallizes. The crust fractures because it must adjust to decreasing volume. Scarps rise where compression exceeds rock strength. These are mechanical responses to cooling, not symptoms of collapse. Over billions of years, Mercury's radius decreased measurably. Its surface recorded the evidence in thousands of faulted ridges. Its magnetic field persists because some liquid metal remains in motion deep inside. Its poles harbor ice because extreme temperature gradients allow volatile preservation in shadow. Each phenomenon fits into a coherent physical model. There is no mystery in the mechanics, only scale. On Earth, tectonics are driven primarily by plate motion and mantle convection. On Mercury, tectonics are driven by contraction. On the Moon, contraction occurred earlier and more completely. On Mars, contraction interacts with localized volcanism and crustal dichotomy. Every rocky world expresses cooling differently. Mercury expresses it clearly. Its large core relative to its size amplifies contraction effects. Its thin mantle provides less insulation. Its proximity to the Sun eliminates atmospheric buffering. Its small size accelerates heat loss. These factors converge into a simple outcome: structural adjustment. Looking forward, Mercury's future unfolds along predictable lines. Internal heat will continue to decline. The remaining molten portion of the core will gradually solidify. If the magnetic field depends critically on that liquid outer layer, its strength may diminish over time. Eventually, dynamo action may cease entirely. When that happens, Mercury will lack even its modest magnetic shield. Solar wind particles will interact directly with its surface, sputtering atoms into space. But without an atmosphere to erode, this interaction changes little in structural terms. The surface will continue to accumulate impact scars. Micrometeoroid bombardment will grind rock into regolith. Thermal cycling, extreme heating and cooling during its 88-day orbit, will fracture exposed material slowly. Yet none of these processes will alter the planet's fundamental shape. By the time the Sun begins its red giant transformation, billions of years from now, Mercury will likely be geologically inert. Its tectonic adjustments will have slowed to near zero. Its interior will approach thermal uniformity. It will be a compact, metal-rich sphere orbiting an aging star. And then the Sun will change. As hydrogen fusion wanes and the core contracts, the Sun's outer layers will expand outward. Luminosity will increase dramatically. The inner solar system will become hostile in ways far beyond current conditions. Whether Mercury is engulfed outright or drawn inward through tidal interactions remains a matter of detailed modeling. But the probabilities favor destruction through stellar expansion. If engulfed, Mercury's rocky crust would melt rapidly. Metallic components could vaporize or disperse into the Sun's outer envelope. The distinct planetary body would vanish. Yet even that would not be violent in a cosmic sense. It would be part of stellar evolution, the recycling of planetary material into stellar layers. In this long perspective, destruction loses its emotional weight. Mercury's existence spans billions of years. Its contraction unfolded slowly. Its final fate will arrive long after any trace of humanity remains. Time reframes drama. There is a deeper lesson embedded in Mercury's story. Planets are not permanent. They form from accretion in protoplanetary disks. They differentiate internally. They cool. They evolve. They stabilize. Eventually, they are altered or destroyed by stellar processes. Mercury's small size accelerated its aging, but the trajectory is universal. Earth will one day cool as well. Plate tectonics will cease. The magnetic field will fade when the core solidifies. Surface renewal will stop. Long before solar expansion, Earth's geological dynamism will decline. Mercury shows us that outcome in advance. It is not a failed planet. It is not collapsing. It is simply further along the thermodynamic curve. In the absence of atmosphere, erosion, oceans, or biological cycles, Mercury presents an almost pure example of planetary cooling. Its cliffs remain visible because nothing erases them. Its magnetic field persists faintly because some molten metal still circulates. Its orbit remains stable enough to preserve long-term structure. The narrative becomes clear. Energy leaves, structure adjusts, equilibrium approaches. There is a certain quiet elegance in that process. We often think of planetary science in terms of cataclysm, giant impacts, asteroid collisions, supernovae. Those events are dramatic but brief. The dominant force shaping planets is far more subtle. Heat transfer. Heat flows outward. Materials contract, stress builds, rock yields. Repeat this over billions of years, and our world reshapes itself. Mercury's visible surface is a map of that repetition. It does not require myth or exaggeration to be compelling. The physics alone is sufficient. A metal-rich planet, born from violent collisions in the early solar system, cooled faster than its larger neighbors, its core solidified inward, its crust compressed, its magnetic field flickered into persistence, its poles trapped ice despite infernal daytime heat. Now it waits, stable but aging, orbiting a star that will eventually outgrow it. When we step back from the phrase slowly destroying itself, the meaning becomes precise. Mercury is not being undone by external force. It is not crumbling spontaneously. It is transitioning from a higher energy interior state to a lower energy equilibrium. In thermodynamics, that transition is inevitable. Destruction implies chaos. Mercury's evolution is orderly. There is no urgency in its contraction, no countdown to collapse, only gradual adjustment. In the grand scale of cosmic time, planets are temporary configurations of matter orbiting stars that are themselves temporary. Mercury's journey, from molten beginnings to rigid maturity to eventual stellar consumption, follows that pattern faithfully. And in that sense, its story is complete. Not because it ends soon, but because it fits perfectly within the physics that govern all worlds. Mercury is not destroying itself in anger or instability. It is aging. And in the silence of space, aging is simply another form of balance.